Hey everyone, I am Ashish. Welcome to the AI Bootcamp. So today we'll be doing some hyperparameter tuning. Let's go do some hyperparameter tuning. So first of all, like usual, we're gonna go to the website cookiesensei.com and then we're gonna launch the labs. Right over here, we have this button at the middle which says Open Code Server. I hope it's visible now. Upon clicking it, entire VS Code opens. As simple as that, right? You don't need any Python installations or anything. Okay. So far, so long. Let's discuss what we have like discussed so far. So we were talking about regression in the previous chapter. And regression basically is that you take some data and use that data to predict some numerical value. Again, I'm taking some data, using that data to predict some numerical value, right? Okay. And then we talked about overfitting, underfitting, and so on. Did we also talk about that pipeline kind of class? Let me see. We should have talked about pipeline by now. Yep, we have talked about pipelines as well. Okay, so let's go and discuss this project of California house price prediction. So the data set is available on the internet for free. Standard imports. Loading the dataset, dot dot means go back one folder, then allocate datasets, and then housing.csv. If you go back one folder, you will find datasets folder, and over there you will find this housing.csv. So, okay, I'm loading the data. And first of all, this is right here, some missing values I've seen. So missing values, like say, in first few columns, there are 20640 non-null values and float. But over at this column, total bedrooms, there are only 20433 non-null values. There's a better way of checking missing values as well, which could be is null dot sum. So we have 207 missing values in the total bedrooms column. So we will be filling this missing values with either the mean or the median or maybe some manual value. All right, so some exploratory data analysis and visualizations. Basically, it is used to see what kind of data we have. Like over here, longitude, latitude, and housing median age looks kind of fine, but total rooms, take a look at this graph. This graph is entirely shifted to the left with a tail on the right. So I think this is called right skewed. I might be wrong. Could be left skewed. I usually get confused with these two terms. But my point is that this particular column needs some pre-processing for the model to perform better. Take a look at this column as well. Same behavior is happening. We have a tail on the right. Same for this, we have a tail on the right. And same for this, we have a tail on the right. Same for this, we have a tail on the right. So point is, we need our feature set to be normally distributed, to be in a shape where there are like a well-shaped curve they are forming. Why so is because if you give the model this kind of value, let's say you give total rooms, then I believe there are only couple values for 40,000, but more of the most of the values lie between 0 to 1000, 0 to 100, 10,000, 0 to 10,000 in the range. So the model will be biased against the 40,000 value, meaning that model might not even predict the 40,000 kind of value correctly. So you need either log transformations for it or exponential transformations, whatever I mean would work in this case. But we're not gonna do the statistical analysis right now. We're gonna simply just take a look at the data. That's it. And over at this distribution of house prices, median house value column, we can see that the price is capped at 500,000. Therefore, the last bracket, the last bar is so high. Let's understand the data. In the data itself, we have geolocations, how old a house is, now total number of rooms in a particular town, total number of bedrooms, population in that particular town, households in the town, median income of people. I believe this is in thousands, so 8.3 means 80,000 something dollars. Median house value again in dollars. Ocean proximity is a categorical column. Let's look at ocean proximity as well. Housing dot housing get me the ocean proximity column and count value count. I remember this method. So take a look. We have a lot of data for this category, this category, and this category. But for the island category, we have only five columns. We will discuss more later on in the next topic, in the classification topic, like why exactly do we need our data to be very much equal in all the categories. But the point is, right now, as of now, we can observe that okay, there is something wrong with the data itself. So either you drop this particular category altogether, drop it and fill it with the nearest kind of value that you can imagine for it. Like let's say near bay, near ocean, inland. Inland suggests that it's land, and island also suggests that it's a land. So I could really replace these five categories with inland only, and that would be fine. Okay, so just like we talked about that, island has only four or five data points. And then take a look at the correlation graph. Correlation means that if one variable goes up, another variable also goes up. If one variable goes down, another variable also goes down. So correlation means two variables are somehow related. I'm not gonna use some statistical terms. I'll just say that two variables are somehow related to each other. And we don't want our model to do something like that. And in the next video, I will make sure I will explain all these things properly, like why we don't want correlation, why the data needs to be transformed in a bell-shaped curve, and so on. So take a look. These red data points are all where there is 100% correlation. Of course, like take a look. Longitude is 100% correlated with itself, right? So 100% correlation is okay over here. But take a look. This whole region has the red kind of correlation color. So that means total rooms is correlated with total bedrooms, which also makes sense. Like in a town, the more number of total rooms there are, the more number of total bedrooms there are. And so on for the population as well. So on for the households. The more the population, the more the number of total rooms. So it's advisable at this point to delete three out of these four. Am I making sense? Like delete so that there is no correlation between these things. But we won't do that again. This is a very basic level tutorial. We are gonna do proper machine learning, meaning that take the data, give inside the computer, and let the computer handle everything else on its own. I don't care at this moment to optimize the performance of the model. All I do care about is how to create a model, how to create a machine learning model that learns from the data and make a prediction. That's it. Optimization is something I would say advanced part because statistical analysis comes in over there. So, yep, that was the EDA error checks. So with this line, housing, get me the total bedrooms, fill the missing values with this thing. And what is this thing really? This thing is 45, meaning that calculate the median value of total bedrooms column and use the median value to fill all the missing values inside the total bedroom columns and replace this entire structure, save this entire structure. Now that you have a column, save this entire structure as a total bedroom column, which already exists. So we are kind of replacing the original column that we have. We could have created our own new column as well, but we don't want that. Then we have uh, one hot encoding. One hot encoding goes something like this. So pd dot get dummies. Let's just copy paste this entire thing. We will discuss more about what's going on. Housing dummies column. This it's showing me key error. Okay. Mm, Let me restart the entire kernel again. Again, it's giving me an error saying, let's see, raise the key error. It's not able to find ocean proximity. Why not? Why not? Exactly, why not? Okay, there's another way of doing, I don't remember these syntaxes kind of thing. So let me just Google search for you. And it's a good thing that I'm getting an error right now because perhaps you might also get this kind of error. So let's go to Google and search sklearn. What were we doing? One hot encoder. Basically, over here now, I wanted to test out pandas get dummies function because it's a little easier to test. But then again, I usually always use one hot encoder from scikit-learn. So let's use that only. So in first of all, we have the import statement. I'm coming to the point like what exactly this is. Then I will create a variable. Let's say I'm creating a variable of apple. I'm calling the class one hot encoder and also x.fit. Okay. So apple dot fit. Take a look at the data, which is this thing, housing and the ocean column. Ocean proximity. All right, I see what's going on. I changed the values. I see actually over here now what happened was now I see the error. If I print out the housing now, it has already done for me the one hot encoding. That's why it's not working. That's why there was the error. So already what I did was I said pd.getDummies. Over here, let me do that. pd.getDummies on this thing. And I will say run all. So what happened was initially our data frame was something like this. Initially, the data frame was something like this. Uh, Actually, I shouldn't have used the same variable name. That's why so many errors are coming up. So ocean proximity was carrying some categories. So our let's say our mathematics allows us to use numbers, to use variables, but not categories like this. So what we do instead is we convert them to zeros and ones. Basically, false means zero and true means one. So either true false, either in a Boolean form, it is fine. It is fine if there were a zero and one. So what we did was we converted the first column of ocean proximity into, take a look, this thing, ocean proximity less than 1 h ocean, and all the categories are right here. And wherever the category is, so the first category is nearby. So see, nearby is true and all other categories are false. If you just look at the ocean proximity column, the first one, two, three, four, five, six, first six values are nearby only. So therefore, you will see that first one, 2, 3, 4, 5 values are nearby. So one hot encoding means that there is only one hot feature, one particular feature only that is true. Otherwise, all the features are false. So anyway, let's continue and let's use the one hot encoder part. So no, let's not use it because we have identified the problem. So yeah, then we are doing a train test split. Then we are training some models of linear regression, decision tree, and random forest. Basically, where did I find this code? Is from the scikit-learn documentation itself. Regression. You go to scikit-learn documentation, click on regression, and you will find all the models that you might need. So linear models right here, quadratic discriminant analysis, whatever that is. Decision trees right here we have. So all the import statements are right here. So you don't need to worry about like what's the kind of where did I find the syntax? But a basic scikit-learn syntax is import the statement, call the class, instantiate the class, dot fit, meaning that take a look at the data, and then dot predict. And then I'm calculating the root mean squared error, which just means that remember the error that we discussed when we were talking about salary versus a work experience data, that we were talking about some error measure that take a actual minus prediction square, add them up, then take a mean of the entire thing. And if you take a square root, that becomes root mean square error. We are taking the square root because we actually took a square as well. So there are different measures. You could have very well chosen mean square error as well. Over here, it's just that I'm choosing root mean square error. You could very well do the complete analysis with mean square error. It will be totally fine. It's totally up to you which error measure you are using. So over here, we are choosing R2 score and root mean square error. Then we are training random forest model. Same kind of API is there. You import, you call it, you train it, you predict it, and then you calculate the root mean square error, then R2 score. Same for the any kind of basically model that you have. KNN, support vector regression, and then all I've done is created a data frame out of this thing so that I would be able to see like, okay, which model gives me the highest R2 score and the lowest RMSE value. Lowest error and highest R2 score is given by random forest. And basically random forest, if you want to have an intuition, then random forest would be a collection of decision tree regressions. And if you don't understand what I'm talking about, you don't really need to at this moment. It's just that there are different algorithms. Decision tree, bigger decision tree would be a random forest, and sample models they are called. So let's do this entire thing with a sklearn pipeline kind of structure, and we will do the hyperparameter tuning as well. That's the main catch. That's the main part that we're gonna do. I mean, right now is the main part that we were supposed to do in the beginning. So import statements, load the dataset, split, or what do you say, bifurcate the dataset into X and Y. Then X dot select D types include equals object would take all the categorical columns. X dot select D types exclude object would take only the numerical columns, and we are using dot columns, so we are only taking the column names only. We are not taking entire columns. Then we are creating a pipeline. Then we are saying simple imputer. Remember the simple imputer I was talking about? No, I was not talking about simple imputer. I was talking about one hot encoder. Anyway, the simple imputer is just to fill the missing values automatically. So in the numerical pipeline, what I'm gonna do is I could have very well put apple, mango, guava, tier, anything over here. So I'm creating a pipeline which says wherever you find a numerical column over there, if you have a missing value, fill that missing value with that column's median. So if there are two columns, fill first column's missing value with first column's median. Fit second column's missing value with second column's median. I hope I made some sense. Then there are some categorical pipelines. So in the categories, first of all, fill the missing value with the mode, which is most frequent value. Then do the one hot encoder. And remember, it's the best practice to do the drop equals first. And why is that so? It's because the full explanation will be given in the next video. But at the moment, the intuition would be it's a best practice to drop the first, because if all the let's say there are total of five categories, and if you have chosen all the five categories without dropping the first column, all of the five categories would be like, let's say, my third category, in my first row there is third category, so the entire one hot vector would be 0 0 1 0 0. So five values we have: 0 0 1 0 0. The entire vector is of length 5, and because we have category 3, so in the third position we have one hot vector, one hot numerics: 0 0 1 1 at the third place, one hot feature, that is. So the point would be, my if I take all the five columns in a one hot vector of 5 length, then everything is logged, everything is correlated. If this is one, rest of the others are bound to be 0. If one category is 1, the rest of the categories are bound to be 0. So that's why, in a nutshell, we, as a best practice, we use drop equals first or drop equals last. Then we have a column transformer to transform the columns. What we will say is, hey, numerical pipeline, be applied upon numerical columns. Hey, categorical pipeline, be applied upon the categorical columns. And then the full pipeline goes something like this. This preprocessor, first of all, preprocessor dot transform will be called. Then random forest regressor dot fit will be called. Dot fit dot transform. Hmm. Let me take a look again. So yeah, pipeline. So both of these need to have the dot fit method. So preprocessor dot fit, random forest regressor dot fit, and when you call it somewhere along here, let me show you. Pipeline is there. So what I will do is pipeline dot fit. I will do somewhere pipeline dot fit train test split. And oh yeah, I have shown you the pipeline kind of structure before as well. So let me show you this time this thing, hyperparameter tuning. So there is something called randomized search CV that will take a model, and that particular model needs to have a dot fit dot predict kind of structure. So in this pipeline, this thing has a dot fit dot transform. This thing has a dot fit and dot predict. So combined, it gives me the pipeline. So pipeline, give me all the possible parameters that we have for the random forest model. And where did I get these parameters from? Over here. So if I say random forest sklearn, random forest regressor, I go over there and let me scroll down a bit. I found all the categories over here only. It's not like I remember them. Now do I need to get params, predict, score? Okay, where are all the uh, somewhere in this page only I found out. Oh yeah, right here it is now. Number of estimators. In the first line itself, it was skipped. Number of estimators, like how many number of trees do you want? It is number of trees or what? Number of trees. I think so. It is called number of trees. Let's check. Number of trees in the forest is number of n estimators. Yep. Criteria, max depth, like how long you want the tree to be. Minimum sample split, how many minimum samples do you need to have a slit, and so on. There are a lot of parameters you don't need to know understand like at the moment, like what all these parameters do, because this is a hands-on. So over there, what I found out was a model and estimators. All right, 100 estimators, 200 estimators, 300 estimators, 400 estimators, 500, I mean. Then max depth should be none, 10, 20, 30, and so on, so on, so on. All right. And then I'm taking that randomized search CV Take the pipeline. This is the parameter distribution. This is the parameter distribution. And number of iterations, I want it to do four number of iteration with cross validation of two. Cross validation basically means if you're seeing the training data set, split the training data set into two parts. Use one part to train, use another to predict, then use another to train, use the first one to predict. So that's what cross validation means. I'm on purpose keeping these values very low because let's say if I keep them very high, system will become very slow to run. So that's why I'm choosing for it to be 4 and 2 so that there are only 8 fits. See, fitting two folds of each of the four candidates, 8 fits. Random search dot fit. So I'm calling this randomized search random search dot fit. There's a dot fit method. So fit appropriately. So what will happen in this pipeline would be that first of all, the data would come in, and because there is this entire pipeline I'm choosing, this pipeline will first of all, the data will go into the pre-processor. Then the data will go inside the column transformers and transform the numerical and categorical columns according to what numerical columns and categorical columns names are passed. And in the numerical columns, only simple imputer is going, which means that fill the missing values with median. And in the categorical columns, fill the missing values with most frequent, and then one hot encode as well. So create one hot feature vectors from the categories. And basically at the last we have our random forest regressor. So then at the last, use this random forest regressor to dot fit. So when I write random search dot fit, all of these things are happening at the like first of all, pipeline dot fit is happening. Then pipeline dot fit. Let's say randomized search. What it will do is at the random it will take this parameter, this parameter, this parameter, this parameter, and this parameter, and using those parameters it will calculate one fit and so on. So randomly it will select four options, four best options randomly it will select from the parameters. So after that, you can see the best parameter model is model and estimator with 300 trees, minimum sample split of 5, minimum sample leaf of 4, and so on. So I know it might be confusing, but if you try it on your own, then I believe it will be very much understandable. All right. So I'll see you in the next lecture where I will be discussing more theory about all of the things that we have discussed in the